So 6.6 is on applications, particularly the distance, rate, time problems. So distance equals rate times time. If you solve for distance, it's distance equals rate times time. If you solve for a rate, it's the distance divided by the time. And if you solve for time, it's the distance divided by the rate. And so keeping track of your stuff in a table like this can be helpful. So identify what your variable is for word problems. And that comes from the question part. So it says, what is the speed of the boat in still water for this example? So your variable would be representing the speed of the boat in still water. And you can use any variable you want, like X is pretty typical. With word problems, I typically use letters like R for a rate, or, you know, you saw me using D for dimes and N for nickels, like something that represents that. So I use R because it's the speed is a rate. So I fill out this table for both scenarios. So this one is about going against the current and with the current. So when you're going against a current, your speed is being slowed down by the current. But when you're going with the current is helping you go even quicker. It's working with you. So that's why the speed of the current affects the speed that you're going to be able to go. So here's your rate in still water, but because it's not still water, if you're going against, you're subtracting that current, and if you're going with the current, you're adding that current speed. So a boat travels 30 miles upriver, so the distance is 30, in the same amount of time. So there's where the equation comes in. Same amount of time. Same means there's an equation, there's an equals. And that it takes to travel 50 miles down the same river. So 50 miles is the distance for going down. So I do the rate that the boat's able to go going up, the rate in still water -5 because it's going against the current when it's going upriver, and then rate in still water +5 when it's going down because it's going with the current. So then your time is your distance, which you were given, divided by the rate, which we wrote here in terms of R. That's what we're going to solve for. And I can set these times equal because the problem said that it takes the same amount of time for these two scenarios. So then I have an equation, and from there it's what we've been doing before. So the new part for this lesson is the setup of the equations. So once I have my equation, I can use the LCD method to solve. And then again, write it in a sentence. Just like before, we have distance. In this case, it was distance going up and down were both 12 miles. Going against the current, so -3, current was 3 miles per hour in this problem, and with the current +3 for downstream. Time is distance divided by rate, and it said that the total, so total is 3 hours. So the time part will add up to 3 hours. So this time going upstream, this time going downstream is a total of 3. Upstream plus downstream equals 3 hours in total. So there's your equation, and then you apply the same technique as we did in 6.5 to solve it. LCD to both sides. Then we have a trinomial here, quadratic, highest exponent is 2, trinomial that we can solve using the factoring techniques from chapter 5. Factoring out the greatest common factor, factoring this trinomial further, we have R is -1 or R is 9. Except the problem is that R could not have been, the rate cannot be 3 or -3 because that would mean we're dividing by 0. It also can't be negative because of context. You cannot be having your boat in still water go negative miles per hour. So you're left with a rate of 9 miles per hour in still water. So there is extraneous solutions for context. in this problem is what I was illustrating there. This is another example of it being the same amount of time, so it's pretty similar to one of the other examples I gave. The difference here is that we don't have a rate of a current affecting both directions. It just has the second car is traveling 6 miles per hour slower than the first. So if R is the first car's speed, then 6 miles slower would be R minus 6 for the second car. And so it's a slightly different setup in terms of the rate because it's only affecting one of the vehicles. And similarly here, this one was going to drive faster to make up some speed, so it was going faster than the other by 5 miles per hour. This one also had a different scenario where it wasn't the same amount of time. It was that there's a delay, and so there's an example in the book similar to this as well. The normal time is equal to your delay plus this week's time. That's how you set it up and then solve with the LCD method from there. Another scenario that can come up is maybe the distances are the same. And so here you were told about the time and the rate, again with current and without current. And so your distance is your rate times your time. So I did these multiplied together for the distance, these multiplied for the distance. And then I'll set the distances equal because it says same in distance. So that means equal distance. So this equals this. And then I can solve that linear equation. So that's kind of the setup on these. And then the solving is either a linear equation or a quadratic equation where you may have to use the LCD to clear fractions. It's a very brief overview, but I hope that helps get you started on those problems. Did you have any questions right now on that section?
No.
Yeah, you haven't gotten there yet. So if you do end up having questions, feel free to message me.
Okay.
All right, that's it for tonight. I'll load 6.1 and 6.2 and all the rest of these in tonight and tomorrow. It'll take some time to upload them.